Alright, hello and welcome to my video on the difference in differences method. This is going to be a very different video than my previous ones on kind of more philosophical topics. This is going to be more economics, mathematical, statistics based, but it should still be interesting, and if you're interested in the philosophy of causality, it should still be of note to you. But otherwise, I think you'll learn a lot, even if you're not specifically interested in this topic. So without further ado, let's go ahead and get into it. So first I want to kind of outline my goals with this video, and what you should learn and where you should be able to go after this. First, I think I just want to outline difference in differences and show the kind of intuition behind it, like what exactly it's doing, what problem it's solving, etc. From there, we're going to discuss Card and Krueger's famous 1994 minimum wage paper. Then we're going to gain a more formal understanding of difference in differences, looking through the potential outcomes framework. We'll take a brief look at event study plots, and finally we'll cap it off with a discussion of Currie and Thomas's Head Start paper from 1995. This is another difference in differences paper, but it has some striking differences which I think help to kind of illuminate what exactly difference in differences is doing. After some careful watches of this video, I think ideally you should be able to go and read a paper on your own, really. That might require going through this with pen and paper once or twice. It's going to be a long one, so strap in, but I think it'll be very informative. So first, we have to talk about Jon Snow. Do I mean this guy? No. I can tell you this guy has done nothing interesting or correct. I'm talking more about this guy. This is 1800s physician Jon Snow. And basically, at the time that he was alive, scientists believed that cholera, which if you don't know is a kind of very dangerous illness, was transmitted by air. This was the miasma theory. And Jon Snow, he had a different idea because he was observing all these different inconsistencies, like the way that people would quarantine themselves based on the transmission by air wasn't correct. He noticed that cholera rates seemed to be different depending on where you got your water from. So he basically formulated an alternative hypothesis that cholera was transmitted by water, okay? And he wanted to test this, like a good scientist, he wanted to test his hypothesis, and he was actually presented with an opportunity to test his theory. In the 1850s, one water company moved its pipes upstream on the river that they were pumping water from, and they moved it to a cleaner portion of the river. One of the other companies that was very similar stayed exactly in place where it was, in the polluted part, right? So this gives him a kind of natural experiment to study, like one moved up, one stayed, and let's see if this affects cholera rates for the one that moved. And so he did a lot of footwork, he did a lot of numerical calculations showing that they're very similar initially, and basically he was able to show that the shift of pipes saved 78 lives, okay, so that's huge, 78 lives per 10,000, and also proved the cholera transmission by water, so we don't even know how many lives he saved because of that, really. And it introduced us to the rudiments of the difference in differences technique, which, obviously is the most important part of this, right? But obviously this example is a little bit kind of old and it might not be relatable, so let's shift to a more modern, politically charged topic. Let's get controversial. So, what is the effect of the minimum wage on employment? And I have here this classic, Econ 101 graph, right? We have supply and demand. When the minimum wage gets instituted and it's binding, it starts a price floor, and because of that we have a shortage of jobs because more people want to supply their labor, but less firms want to supply jobs at that price. And basically, employment is predicted to decrease. This is the classic theory, and for a while, it was kind of uncontroversial. However, when looking at the actual empirical work studying the effects of the minimum wage, we see some key differences. So basically, if you're studying teenagers, you actually do find this negative effect. And keep in mind, this is pre-Card and Krueger 1994. You do find the negative effect that you'd expect. But this is actually in opposition to earlier studies of teenagers, which were finding no negative effects. So already within teenagers, who you'd think would be most affected by a minimum wage increase, there's already this kind of controversy about what the effect is. Okay? And then, right before Card and Krueger, a bunch of these recent studies showed that there were basically no negative effects. We can see Card and Krueger's name already showing up here. They've been studying this for a while. No negative effects. The scene at this point is that there's basically this paradoxical clash between theory and evidence. Okay? So their source of variation in the paper is in 1992, New Jersey raised its minimum wage from $4.25 to $5.05. Okay, this is a pretty substantial minimum wage increase, and New Jersey actually knew about this increase for 2 years, keep that in mind, before it was going to happen. Spoiler alert, obviously the results are going to be counterintuitive, and they're careful to say at the beginning that this happened during a recession, so results aren't due to some economic growth that was lifting all boats, basically. We're going to use a control group of similar stores in Pennsylvania, and then higher wage stores in New Jersey. Now, you may be thinking, how is Pennsylvania a good control group? Well, actually, Difference in Differences has a different idea of what a control group even means, and we'll talk about what exactly that consists of. Okay? And yeah, we're going to argue that Pennsylvania will be a valid control group. Okay? So how do we even study this? How do we study the minimum wage's effect on employment? Well, to do that, let's introduce a easy kind of framework to study the dynamics of the minimum wage on employment. Okay? So we're going to let NJ be the treated group and P be the control group. Obviously, NJ here is New Jersey, P is Pennsylvania. We're going to study outcomes, aka employment, in 2 periods, before and after. And this is referring to before and after the treatment. We're going to apply this treatment, W, which stands for wage, just to keep that in mind. It's going to apply only to New Jersey in period 2. So we're only going to see the effect of the wage in New Jersey in period 2. Each group has a level, and these can be different. That's the key here. These can be different levels initially. So normally you'd think you'd want Pennsylvania to be the exact same as New Jersey in a kind of ideal control group. But here, Pennsylvania's level is allowed to vary. But each of them will have a pre-period employment level, if you want to think about it like that. So this would be full-time employment in both. And we have this parallel trends term. Both would change by T if W equals 0. So what this means is that if the minimum wage was not applied to New Jersey, then in period 2, we would just see NJL plus T and PL plus T. Basically, they would both go up by 5 if T equals 5. And keep in mind here, T does not equal treatment, T is trend. All right, W is the treatment. Okay, and another key assumption, we have that W has no effect before period 2. So this just means that, New Jersey knew about the minimum wage increase for 2 years before it happened. This basically says that they didn't do anything in anticipation of the future change. If they end up not getting the minimum wage, or they weren't even announced to get it, they weren't assigned the treatment, this would have no effect regardless. Okay, now that we've got that out of the way, let's think about how we're going to look at this. So one way we could do it is if New Jersey raises their minimum wage, can we just compare employment levels before and after the treatment? This seems kind of intuitive. You can just say, oh, it increased, so therefore it's the minimum wages effect. Okay? Let's look at this in a simplified table. The idea here is that if we have before and after, you can see here we have before, here we have after. So in the before period, we just have our level of employment NJL, but then we go to the after period and we have NJL plus T plus W. So the problem with this, obviously, is that we have this simultaneous trend term, W. We have the simultaneous T that isn't able to be differentiated from the minimum wages effect on employment, W. So if we just compare before and after, we're unable to isolate the effect of W on employment, which actually W is the effect on employment if we're talking strictly potential outcomes. So this method is faulty, and we can look at a kind of regression that does the same idea. This is just reprinted. Here we have a kind of simple 2-point regression. Again, we just have a point before and a point after. This is our outcome. This is our constant. If you think y equals mx plus b, this is just b. This would be our m. This is the slope going from period 1 to period 2. This variable after is actually an indicator variable that turns on in period t equals 2. Okay? So this is just, if we have 2 points before and after, we're just connecting a line between the two. So hence why there's no error term over here. Okay, and the way that we outline this is very similar to what's up here. So A here is just NJL. This is just the level that we get in the pre-period, and then we get plus B, the effect of going into period 2. If we difference them, we get B. So we'll get an estimate for B, but this is not the true effect of the minimum wage on employment. It's T plus W. And again, the reason this doesn't work is because we have simultaneous trends. We can't differentiate the effect of the minimum wage on employment. Another way we could do it is if we just look post-treatment at a state with the increase and a state without it. So if we just compare in period 2, New Jersey and Pennsylvania, and see if there's a kind of differential thing going on here. The table that looks like this is supposed to outline it. So here we're looking at after for both periods. We have New Jersey and Pennsylvania. And we have NJL plus T plus W. Remember the second row from the last table. But for Pennsylvania, we just have PL plus T. So they don't get W. And if we just take the difference between these two, YNJ minus YP, we get NJL minus PL plus W. So we were able to get rid of this trend term, but we see that there are these state-specific effects, or these state-specific levels that aren't differenced out. And again, we're unable to isolate the effect of the minimum wage on employment. This can be done with a similar two-point regression where we just have one dot, which is Pennsylvania's outcome, and New Jersey's outcome is the other dot. This is the two-point regression, so we have y equals mx plus b, a is again b, c is m, it's the slope, and then this variable is a New Jersey indicator variable, so if you're in New Jersey, you get turned on. So this would be like our second dot, basically. And we can see that New Jersey gets A plus C, whereas Pennsylvania only gets A because this is 0 for Pennsylvania. Okay, and if we difference it, we get C. So again, we get an estimate from this regression, but we know that this C does not equal the effect of the minimum wage on employment because we're unable to difference out these state-specific effects. Well, how do we actually do this? The answer is pretty simple. We just combine the two. We literally do before and after and New Jersey versus Pennsylvania. So what we're doing here, let's first look at New Jersey. So we have our group New Jersey, and then we're going to do before and after. This is the first table that we saw. It's just NJL, and then we have NJL plus W plus T. So NJL plus the treatment plus the trend in period 2. If we take the difference between these two rows, as we did before, we get W plus T. So we have the treatment effect plus the trend effect. Okay? Keep that in mind. Here, we're looking at Pennsylvania. Before, they just have PL. And then in the second period, they get PL plus T. So we go up by the trend. And if we take the difference, we're able to get rid of the state-specific effect, PL, and we just have T. Now, if we take the difference again, so we're taking the difference in these differences. Remember, these two are differences, and we're taking the difference in them. This is difference in differences. Okay? Very simple. And if we do that, we subtract out this T, and we get W. So this method, by differencing out both before and after, and treatment versus no treatment, we get the effect of the treatment on the treated. Okay, I hope this makes sense, and we can do a very similar regression that we did for the other two. Okay? But this will have 4 points, so we're going to have an error term now. And again, I know this looks complicated, it has Greek characters, but it's the same thing. So we have our outcome for individual I in period T. I didn't touch on what I means, but basically it's just the individual, or we could do S for state. So this is New Jersey or Pennsylvania. And then T is just our time period. T equals 1, T equals 2. Now this combines the previous two regressions in a very simple way. This is just our constant. This is our B from y equals mx plus b. Okay? This is just an indicator that turns on in period T equals 2. So both of our individuals will get this because this is only indexed by time. This gamma times NJ will only turn on for New Jersey in both periods. It's not indexed by T, it's only indexed by I. And then this delta times after T times NJI will only turn on in New Jersey in period T equals 2. Okay? And then we have our error term. We're going to kind of ignore the error term for these outcomes. But if we look at this in our chart, it's very similar to what we had before. In New Jersey, in the before period, we have alpha plus gamma. So we have our constant plus the indicator for New Jersey. Remember, this isn't indexed by time, so they get it in period T equals 1. And then in the after period, both of the other variables turn on because we have after sub T. So New Jersey gets lambda plus delta here. Okay? And Pennsylvania, we just have alpha in the first period because they don't get this. They're not in period T equals 2. They're not in New Jersey, and both of these are 0 here. So we just have alpha. And then in the second period, we just get lambda because over here, they're not New Jersey. So we have alpha plus lambda. If we take the difference, again, we have lambda plus delta and then lambda. You can already probably see that lambda is basically T from the last period. Lambda is the trend effect. And that's why it's what happens between period T equals 1 and T equals 2. It turns on in T equals 2. And delta is our treatment effect. This kind of assumes that there's nothing else going on between periods T equals 1 and T equals 2 in just New Jersey. We have lambda plus delta and lambda. And then if we subtract the 2, we get delta. Now, I put this in Greek characters because I actually took this regression and the upcoming graph from Scott Cunningham's book. Just want to give him credit there. So let's compare this chart to the last chart. Not much to talk about here, but it's exactly the same. We just have that alpha is PL, alpha plus gamma is NJL, and then we can see an obvious correspondence between lambda and T and W and delta. Okay? So it's the exact same method. Basically, we're just working with the coefficients from the regression rather than these kind of vaguely defined outcomes. So keep this chart in mind. We're going to now reprint it at the top of the next slide and look at a graph that kind of shows exactly what's happening here. So I have this graph, and we're looking at this line right here. This is Pennsylvania's line. So in period 1, they have a higher level of employment, and in period 2, they have a lower level of employment. Now, New Jersey has this level of employment, alpha plus gamma. So it goes from alpha, which is Pennsylvania's pre-period level of employment, and then we go down by gamma. So it looks like they have a lower overall level of employment, but between period 1 and 2, they go up. Okay? Now, as we said, we cannot just compare this point to this point because we have that trend factor that we're unable to differentiate out. So what difference in differences does is that it takes Pennsylvania's line, okay? It shifts it down to align it with this dot right here, okay? And notice that when this line is shifted down, we have this point now basically right here, okay? Because this line is parallel to this line. So once we take this line and we go down to this line, we then have the counterfactual outcome, okay? And this counterfactual outcome is constructed by using Pennsylvania's trend, or lambda, as a kind of synthetic trend for New Jersey's counterfactual outcome, okay? So we assume that New Jersey would have gone down by this much if the minimum wage was not instituted, okay? Now, once we have translated this line down, we just take the simple difference between this counterfactual outcome and this observed outcome, okay? And this is our delta. This is our difference in differences. It's the observed minus the counterfactual. That's it. It's very simple. We're just translating this line down and using it as our new slope for this counterfactual outcome for New Jersey. Okay? And here you can think about this parallel trends when we assume that New Jersey would have moved the exact same way as Pennsylvania as basically some kind of like nationwide or region-wide economic growth or economic decline or something like that. Something that affects them both. So this is basically what difference in differences does. It's very simple. Now, I want to hammer home what delta exactly is. Delta is the difference within the treated group, so we're only looking at New Jersey here, between the observed outcome, this dot, and this like hypothetical imaginary counterfactual outcome. Now, I call it imaginary not because it's not realistic, but more that we don't observe it and we're using Pennsylvania's line to construct it. So we're basically imagining it. We're assuming that Pennsylvania's trend is an indication of what New Jersey would have done. But we're thinking about what would have happened to New Jersey if the treatment hadn't been applied. That's the key there. Even though New Jersey is the treated group, we think about what would have happened if it had not applied. Now that we have this out of the way, let's look at Card and Krueger's actual results. So we can see that they do the exact same thing that we've been talking about. For Pennsylvania, we have 23.33 as the pre-period employment level. And then in the second period, they have 21.17. They just take the difference between these two and they get negative 2.16. And if you remember, this was our T or lambda. This was the trend between period 1 and period 2. Okay? Then for New Jersey, we're looking at 20.44. We have 21.03 as the second period employment level. This is our observed outcome. Okay? And then we take the difference between these two, so 0.59 minus negative 2.16, and we get this number, 2.76. This is one of the most famous numbers in all of econ because it's directly connected with the overall counterintuitive result of this paper that the minimum wage seems to have increased employment in New Jersey. If you're wondering what exactly this number means, we see that 2.76 is the change in mean full-time employment, and this literally just means that it increased by about 3. Now, earlier I said that Pennsylvania will be argued to be a valid control group. We can look at that over here. So these are stores in New Jersey that have above $5 wage, and for most of the stores in this group, the minimum wage was non-binding. So they would get the kind of state-specific effects that New Jersey's lower wage stores do, but they are unaffected by the minimum wage, okay? So ideally, if Pennsylvania is a good control group, we would see similar dynamics happening there. And that's actually what we see. We have 22.25 as the pre-treatment employment level, And then 20.21, we take the difference between these two and we have negative 2.04. So this is pretty similar to negative 2.16. Obviously, it's a bit different. It's not the exact same, but it's enough to show that Pennsylvania likely had similar dynamics to New Jersey, and maybe that parallel trends could hold here. Okay, now that we have these simple results out of the way, let's look at this a little bit more formally using the potential outcomes framework. We can't do this yet because we actually have to introduce these two assumptions from Sattva. So Sattva is the stable unit treatment value assumption, and we basically need this to identify causation. Okay, the first assumption for Sattva is that we have homogeneous treatment. This basically means that if multiple states get the minimum wage, they get the same dose of the minimum wage. Or, if we're thinking medical outcomes, we have the same dose of medicine applied to all the treated groups. And second, we have assumption 2, which is no spillovers or general equilibrium effects. And this basically means that not only does New Jersey's minimum wage increase have no effect on Pennsylvania's market, but there's also no indirect kind of further effects in New Jersey where the minimum wage somehow decreases employment, which lowers GDP, which comes back and lowers employment even further, or something like that. We're just focusing on these direct effects. Now that we have Sattva out of the way, let's move on to the model setup. So we're going to call the treatment DI. And this equals 1 if you're in the treated group. If you're in the group that's assigned the treatment, okay? And it equals 0 otherwise. So if you're in New Jersey, this equals 1. If you're in Pennsylvania, this equals 0, okay? Pretty simple. And we're going to apply this treatment DI between periods t equals 1 and t equals 2. So the treatment effect will only show up, ideally, in period t equals 2. Now we have a balanced panel of groups. This isn't super important for our purposes here, but this is an assumption we have to make. I goes from 1 to n, and a strict subset of those are selected for treatment, meaning DI equals 1 for those groups. The researcher observes Y, IT, and DI. So it observes outcomes for each individual in each time period, and it observes the assignment to treatment. It observes your treated status, your treatment group status. And finally, we're going to introduce a bit of kind of confusing notation. We have YIT superscript 1. This is the outcome for those who are actually treated. And this is the very key thing to understand here. Otherwise, the next section will not make sense. This is the outcome for those who are actually treated. This is different than if you're in the treated group for our purposes here. Because we're thinking about counterfactual outcomes, we could be in the treated group, okay? But we could not get a treatment. So we could be in this YIT0 where we don't get a treatment. So if you remember the graph from earlier, and I'll look at this again, but we had New Jersey not getting the treatment, and that's how we get our counterfactual outcome. This would be that if DI equals 1 for this group. For our purposes here, let's think about there being a difference between being in the treatment group and actually getting the treatment. Those things don't necessarily have to coincide. And finally, our causal effect of interest is just delta, which we had earlier. It equals the expectation of YI21. So this is the group who gets the treatment in period 2 minus YI20, the group who doesn't get the treatment, but given that DI equals 1. So we're saying that for both of these outcomes, you're in the treated group, even though in this one, they don't get the treatment. So this is our counterfactual outcome, okay, that we don't observe. You might be a bit confused, so let's break this down. We have this term. I've just reprinted it here. What exactly does this mean? First term we might want to look at is this E. This is the expectation operator, and because we're dealing with potential outcomes, we're looking at a kind of population term rather than just like an estimation thing. So we have to look at the expectation, but basically this means the mean or the average. So this is like average employment, if you want to think about it like that, okay? E is a linear operator, so we can split this term up, and we'll have E of YI21, given that DI equals 1, minus E of YI20, given that DI equals 1. Second, we have this term, YI21. This is the observed treated outcome in period 2. So this would be employment after the minimum wage increase. Nothing too confusing here. YI20 is the untreated outcome in period 2, okay? If you want to think about it in terms of the graph we saw earlier, this would be New Jersey's counterfactual outcome. But given that we haven't introduced this DI equals 1 yet, this could technically also be Pennsylvania's untreated outcome as well. When we have DI equals 1, this means within the group selected for treatment. Once we have this DI equals 1, we're only thinking about New Jersey, and this becomes the counterfactual outcome. The one we don't observe, the one we're kind of imagining. This E of yi20, given that DI equals 1, is the expected but unobserved counterfactual outcome in the group selected for treatment. So we have DI equals 1, we have DI equals 1. This means you're in the group selected for treatment, but if it didn't actually happen, this is what that 0 signifies. So if we have superscript 0, we didn't get the treatment, but if we have DI equals 1, we're in the treated group, we're in New Jersey. If this DI equaled 0, then we would be Pennsylvania, and this would be uncontroversial. All right, so let's break this down one more time. I have here the graph. You'll have to ignore my bad handwriting, okay? But this is EYI21. This is right here. This is our observed outcome, okay? I've split it up, but this is our observed outcome, this first term. The second term is this counterfactual outcome. So yi20, given that DI equals 1, okay? And then we're just looking at the difference between these two. So I know it's weird that they don't get the treatment, but they're still in the treated group. And our delta, again, was just the difference. So I have here our causal effective interest reprinted. We don't observe yi20 given that DI equals 1. Again, this is not observed. This is our counterfactual outcome. Okay? And the way we would try to solve this is that we would want to compare to an untreated group and try to recover that trend term. But we have to introduce 2 further assumptions, and then we can compare. And these assumptions are very critical. So the first assumption, as I've said before, is this parallel trends term. What we say here is that the expectation of the untreated outcomes for the treatment group, the expectation of the difference in the untreated outcomes. So we have superscript 0. These are untreated, but we're in the treated group. So before, this would be this line, okay? The difference between this dot and this dot. We have that this difference equals the difference in the outcomes for the untreated group, for Pennsylvania, okay? And we have superscript 0 because they also don't get the treatment. So the changes in outcomes, given that you don't get the treatment, even if you're in the treated group, again, are the same for each. This is very critical, and I'll show how critical it is later. We want to note here, first take note that you can split this term up, as I said, and then we can add this term over, and that's exactly what I'm going to note here. I just split. If we subtract this term and then combine them, it would be this right here. If we just add this term over to the right side, we get this. So the untreated outcome for the treated group equals the change for Pennsylvania, roughly, or the change in the untreated group, plus our pre-treatment outcome for the treated group. So what this says is basically nothing specific to either Pennsylvania or New Jersey affected employment at the same time as W. Okay, that's all that means. So there's no strikes going on in New Jersey or something like that, or there's no labor shortage because of, weird legislation in Pennsylvania. I don't know. Could be anything, but nothing specific to either of those happened at the same time as W. So let's visualize this. This is just the difference in the outcomes for the untreated group. This is this dot minus this dot. Okay, so it's just the gap here. And this is the difference in the untreated outcomes for the treatment group. So this is this and this, the difference between the two. Okay? And what we say with this assumption is that these differences equal each other. The gaps are the exact same. And we saw this earlier because we're using this line, superimposing it here, and thinking that that is the change. Okay? So as I said, we can compare to the control group after 2 assumptions. And the second assumption is no anticipatory effects. So looking at the notation, this is the expectation of the pre-period outcome, t equals 1, superscript 1, so they eventually get the treatment, given that DI equals 1, so we're in the treated group. So this is New Jersey's first period outcome. This is this dot right here. And it's equal to the expectation of the pre-period outcome of the untreated. They never eventually get the treatment, but they're in the treated group. So this is also just this dot, okay? And what this basically says is that the treatment only has an effect after application. So if in one world it's announced that I'm eventually going to get a minimum wage increase, and in another world it's not announced, both of my employment levels between those 2 worlds are going to be the same. I'm not anticipating getting a minimum wage increase, and I'm not adjusting because of that, basically. So one thing to think about here is that New Jersey actually knew about the minimum wage increase for 2 years. Did they adapt beforehand? Did somehow firms adapt and were able to intake more employees after somehow? I don't know. Okay, let's visualize this. So I have just reprinted New Jersey's 2 lines here. This is their counterfactual line. This is their observed line. And this left term is just the eventually getting treatment, given that you're in the treated group. So this would correspond to this dot in the sense of this line, this green line. Okay? This, they don't eventually get the treatment, but they're in the treated group. So it's this dot corresponding to this line. And what we're saying is that these are just the same dot, pretty much. Okay? Whether or not you get the treatment has no effect on your outcome in the first period. This would be violated if you think you're going to get the treatment and you start, maybe you already increase your wages or something like that, and it affects your employment level. Now that we have these assumptions out of the way, let's move to the derivation. So, remember what that assumption 1 implied. It implied this term where our untreated treated group outcome in period 2 equaled the change in the untreated outcomes plus our untreated pre-period outcome for the treated group. Okay, so this is just that assumption that we saw earlier back here. I have this reprinted here because we're going to use this in a second, but let's reprint our delta. We're just looking at our causal effect of interest. Again, this is just the observed outcome minus the counterfactual outcome. We don't observe this, so let's try to get rid of it somehow. Let's get this in terms of only things that we observe. As I said earlier, the expectation is a linear operator, so we can split this item up, and we will just have this minus this, okay? Nothing complicated, I just split it up. You can convince yourself that this is the same. Now notice that this term right here is the same as this term, okay? So we're just going to introduce this instead of this. We're going to subtract this and subtract this, okay? And that's exactly what we do here. We substitute in and we have this term. And I have reprinted here what this exactly is. Okay, now we're going to move on. Just remember this term, but I'll reprint it. Okay, remember what assumption 2 says. It says that for the pre-period, given that you're in the treatment group for both, if you get the treatment or if you don't, the outcome in the pre-period is the same. And now I'm reprinting that equation we got from the last term where we have this minus this minus this. Okay, this is our delta so far. Now, what I want you to notice is that this term right here is the same as this term. Okay, so what we do is we substitute this for this. Okay, and that's all we do. We just used our no anticipation assumption 2, and we substitute in directly. I am going to just rearrange this term. I'm going to put it right over here, okay, right after this term, and I'm going to combine. So we get delta equals this EYI21 minus YI11, given that DI equals 1, minus, again, our change in the untreated outcomes for the untreated group. So this is that delta equals the change in the treated outcomes minus the change in the untreated outcomes. So this is our difference in differences parameter. So I just reprinted it here. This is our average treatment effect. Okay, now you might be thinking, how do we estimate this? Just like Card and Krueger did, we just subtract averages, okay? So we have the average for the treated outcome in period 2 for the treated group, minus the average in the pre-period for the treated group, and then we just minus the untreated outcomes. And this is our delta hat. So if we have averages, if we have a sample, we just take the average and then we do 4 means and 3 differences. And similar to before, we can estimate this with this two-way fixed effect regression. You'll see this kind of regression a lot. We have our outcome for individual I in period T. This could also be S. And then we have an intercept. So this would be like NJI we saw earlier. We have intercepts for each individual. And then we have lambda T. So this is like after from before, kind of a funny way to say that, after from before. But yeah, so this is just an indicator for each time period. And then we have delta times our treatment variable. So this turns on and stays on once a treatment is applied. And we're going to cluster our standard errors. This is more of a technical note. You can do more further reading on this, but you do want to cluster your standard errors because we're looking at group outcomes and we're doing this to account for serial correlation. Now I'm going to do some further math and it's not going to be too bad. So we have our difference in difference average treatment effect. Again, just the change in the treated outcomes minus the change in the untreated outcomes. And what I'm going to do here is I'm going to split them up. So I just split up each term. Again, they're just the same. Okay, and we have a plus here because it's minus a negative. And then all I'm going to do in the next part is I'm going to add 0. Okay, so I'm going to take this exact term and then below it we'll have a term that equals 0. All right, so I have this, which is just this, plus some term which equals 0. So it's something minus itself. And this term is E of yi20 given the di equals 1. So if you remember, this is our counterfactual outcome for the treated group, okay? And it's the counterfactual outcome minus the counterfactual outcome. All right, I'm going to reprint this. So it's just this again. And using no anticipation, so by no anticipatory effects, we're going to substitute out this term. Okay, so notice from the no anticipatory effects, this exact term equals this term with the 0. Okay, so we're just going to change this to a 0 basically. Okay, so that's what we do here. We just change this to a 0. All right, I'm going to reprint this. We have this equation that we just saw with this being a 0, and then we have our 0 here plus all this. All right. I'm going to rearrange, and this is very simple. All I'm going to do is take this, and I'm going to put it here, and I'm going to take this term, put it here. All right, so I'm just flipping these two. And what we have here is the observed outcome minus the counterfactual outcome, which as we know is this causal effect of interest, plus, given that you're in the treated group, the change in the untreated outcomes, minus, given that you're in the untreated group, your untreated outcomes. So if you remember, this was assumption 1. This is parallel trends. If we have this, we assume it to be 0, okay? So this is our difference in difference parameter decomposition. That delta, what we estimate, or what we want to see, equals our causal effect of interest plus this extra term, which reflects the kind of parallel trends. And it's the same, I've just combined these two into one expectation. All right? So the key here is that delta equals the causal effect plus some parallel trends term. Okay? Now, again, by assumption, we're assuming this is 0. Otherwise, we have bias, and we need this to be 0 for identification. The kind of true importance of this is that we don't know what direction the bias is. So if we think that our bias would be upwards, that it's increasing the point value of our coefficient that we're going to estimate, but we get a positive coefficient, so we think that our positive coefficient is higher than it should be, the key thing is that it could be a lower positive or it could be negative. So we actually have no indication of whether or not the sign of our estimate will even be correct. Okay? So establishing parallel trends is very, very important. So let's think about a little bit more about what this parallel trends means. We cannot have an endogenous treatment. If your treatment is assigned with reference to a potential outcome, for example, you increase the minimum wage to affect employment because you think employment will go up or something like that. That's endogenous. You need to argue for the exogeneity of D. And in a more concrete sense, basically if the treatment is endogenous, then D and E will be correlated, and you definitely don't want that when you're estimating a regression. Okay, similarly, we don't want any omitted employment affecting variables specific to a state that are simultaneous as the minimum wage, or simultaneous to the minimum wage. We talked about earlier how we may not want like some union strike or some legislation in Pennsylvania, something like that, that's happening at the exact same time, only to one state. Now, one thing you might want to think about is like, okay, if I see that the treated group and the untreated group are moving similarly before the treatment, is that parallel trends? Is that what that means? So can we check the pre-treatment for parallel trends? So the reason that this is faulty is this is a philosophical fallacy. Basically, you say, oh, the past is going to be like the future. Well, why? Because it's always been like that. So it's a circular argument. You're saying the past is going to be like the future because the past has been like the future previously, and so it should happen now. So in the past, it's been like that, and now it should. You can't establish the future from the past. But the key with this line of thinking is that it's convincing. So we can estimate pre-treatment coefficients with this regression right here. We have a similar regression, again, yit equals alpha plus lambda, and then the only difference here is that we have this term. So we're assuming we have multiple time periods before and after. We go back to t minus p if t is the time period that it was applied. Obviously, that's not exactly what's happening here, but t equals 0 could be. So we're going back p, and we're going forward f. So we have p time periods before, f periods after. And we're going to estimate some kind of difference in difference coefficient, delta L, for every single time period before and after. This will make more sense in a second. But basically, we want, in ideal, in a perfect world, we want for all L less than 0, we want delta L to be statistically indistinguishable from 0. And what this means is that there's no difference in differences in the pre-period. So before the treatment, there is no difference in differences. the treatment and control group move similarly. So the dynamics of the treatment and untreatment group are very similar before the treatment is applied. And if we can show that statistically, it's kind of like convincing evidence that they might move similarly after. Now, many will plot these delta coefficients. And let's look at a time series plot of these coefficients. So this is a plot showing a kind of ideal event study, these are called, okay? So treatment, time equals 0. These values reflect time relative to treatment. So this would be 5 periods before, this would be 5 periods after. And why this is ideal is that for every period before, there is no difference in differences, meaning that there's very similar movement between your treatment group and your control group. So even if they have different lines overall, they have similar slopes. They're parallel lines, basically, before the treatment. And then after the treatment, we first have this sharp discontinuity, okay? We have a very quick, sudden departure from these pre-treatment outcomes. And then we have these difference in difference parameters that are very stark and constant, okay? So, key things to grab from this ideal event study is that we have 0 before, sharp discontinuity, and then clear difference in difference effect after. A bad event study might look like this, where we already have a difference in differences even before the treatment. So maybe there's some anticipatory effect here, something like that, or the treatment just had no effect, time equals 0. Notice there's absolutely 0 discontinuity here. This has been the kind of canonical 2x2 before after treated and untreated difference in difference design. But difference in differences is a very, very rich field, and it's getting a lot of attention lately. So where do we go from here? Well, for one, we can add covariates. Notice how we didn't control for anything in these regressions, okay? But we can control for more things and add these into the regressions. We can also change the number of periods and make treatment happen at different times for different individuals. So maybe New Jersey receives a minimum wage in 1992, Pennsylvania gets it in 1993, Rhode Island gets it in 1994, something like that, okay? This might seem simple, and for a long time people did think it was very simple, and they did basically the same estimation strategy, but a lot of work recently has shown that this changes things drastically, actually. Another thing you can do is that you can relax the parallel trends assumption. Obviously, parallel trends is something very hard to establish, very unlikely to hold, so we might want to relax it in some sense. And finally, we can do actually a triple difference. So this would be difference in differences. And the reason you want to do this is because there could be more unobserved heterogeneity that can only be accounted for if you difference again. This is another thing that people have been doing for a very long time. However, it's not so simple, and it's actually econometrically not very well understood. So these would be where to go from now, but I want to bring it home with another empirical example that uses the difference in differences method, but does have some key differences. So let's look at one more example. And this is going to be related to Currie and Thomas's 1995 paper. And they're looking at what is the effect of Head Start participation on education and health outcomes. Now, if you're wondering what Head Start is, it's basically a kind of preschool program that's subsidized by the government. It began in 1964, part of the War on Poverty. And what it does is it provides early schooling, early health care, etc. And it targets low-income children primarily. Obviously, low-income children tend to be disadvantaged as far as early schooling and healthcare. They have less resources to work with. They have poor health outcomes. So this is supposed to be kind of early intervention that provides substantial early human capital benefits. And it's supposed to basically catch up lower-income students and make them on equal footing with higher socioeconomic status students. So the reason this study was conducted is because before Currie and Thomas 1995, there weren't many quantitative studies on the effects of Head Start, despite kind of widespread political acknowledgement of the benefits. You know, it's one of those things where people would say, oh, it obviously works, but when you try to go into the data, there's not much that actually shows it conclusively. So one of the things that people looked at was health outcomes, and these studies were mostly qualitative, not quantitative. And one key roundup of these studies finds that only 34 of 210 actually found health benefits. So even within these qualitative studies, there's kind of weak evidence. There isn't much on schooling attainment, and this is something you obviously want to see in a good study on Head Start. If you're looking at IQ outcomes, these studies were very limited. And one of the biggest things that was cited as evidence for the effects of Head Start comes from the study of a completely different program. So basically, Currie and Thomas saw the state of research at this time. They saw that there's kind of weak evidence for both health and educational attainment specific to Head Start, and they wanted to come in and study it. So they want to see if they can find good quantitative evidence on these education and health outcomes that were absent previously. The first problem, though, with studying this topic is that children are not randomly assigned to Head Start. So already there's a selection problem where eligibility comes from being low income. Kind of by nature of the program, we're already looking at lower income students. Okay? Now, the way that they go about this is that they basically sacrifice external validity, and you look at impacts conditional on familial characteristics. So we're saying, okay, we're only looking at the effects on lower income families. Okay? And you restrict your attention to families where one student attended Head Start and one didn't. So if I have 2 children, one of them goes to Head Start, one of them doesn't. The idea being that, they're similar enough and you can just difference the two and find the effect of going to Head Start. Okay? And that's exactly what they think at first. You take the difference between them and you find the average treatment effect on the treated. Now, let's look at this in the similar table that we saw before, where we have child Head Start and no Head Start. They have the same family effect between them, but the Head Start child should have the Head Start effect. And if you take the difference between the two, YHS minus YNHS, we have HS. So we just get the effect of Head Start. Now, take a second and think about this, why this might not be correct. Well, the first problem is that there could be child-specific factors influencing a selection. I have here CY and CN. This basically is CY, yes, they went, and CN, no, they didn't go. And these are factors that could just introduce a kind of selection bias. For instance, if I choose one child to go to Head Start, maybe I'm choosing them because they're just more capable, or I'm actually choosing them because they're less capable and I want to kind of equalize the 2 students' chances. There could be child-specific factors that, as we see here, aren't differenced out. And if we're thinking about SUPVA, there could actually be spillovers between the children. So if the Head Start child comes home and teaches the no Head Start child, obviously there's a spillover effect and we're not estimating the true causal effect. One of the things that Head Start did was prioritize vaccination, and if parents are exposed to the kind of importance of vaccination, then they vaccinate their other kid. This is a spillover and it's not accounted for in this very simple framework. So I can show this. So we have FAM for both, HS plus CY. So this is the yes, they did go. And then for the no Head Start child, we have the spillover plus the no, they didn't go child factor. And if we take the difference, we have HS plus CY minus CN, the differential between the children, and then minus the spillover. So we're unable to isolate HS. Okay, here I reprint it. We just have this table. And the solution, notice I put a star here, is just to compare to families where one child went to preschool. Okay, the idea here is that the same child-specific factors that go on in which one goes to Head Start are the same as preschool, and that the spillovers would be the same as preschool. So the table is the exact same. I just reprint this one here, and then I have a preschool one down here. So this is the preschool family. This child goes to preschool. This one doesn't. We have FP. This is FAM, basically. So FHS is FAM. This is the exact same as this. And here we have that the preschool child gets the preschool effect. They get the CY, so yes, they did go. The no preschool child has the spillover, plus the no, they didn't go effect. If you take the difference, you get a similar thing here, but it's P instead of HS. And then if you take the difference again, so the difference in the differences, you get HS minus P. So the idea with this is that if HS minus P is positive, if it's greater than 0, it shows that HS has long-term benefits as a premium over and against preschool. One thing to note that's very different than difference in differences is that this estimate is not the average treatment effect on the treated. It's not just the effect of going to Head Start. This estimate is the effect of going to Head Start versus the effect of going to preschool and versus the student who didn't go to preschool or who didn't get Head Start. Okay, this is against preschool. And we do have a parallel trends analog here, which basically says that CY, CN, and S, these terms should be the same between the HS and P families. So between the treated and untreated groups, these are the kind of similar trends going on. So this is like our parallel trends analog. So as before, we can look at their results. We're going to restrict our attention to column 7. So we have 5.875 in the Head Start. This is 6 percentile points, roughly. So for white students, if you go to Head Start, you're roughly getting a higher test score by about 6 percentile points opposed to your sibling who didn't go to Head Start. Whereas for preschool, you just get a 1 percentile increase for going to preschool. So if you take the difference in these differences, you get that it's about 5 percentile points different. So it looks like Head Start did have a large effect on test scores. If we look at black students, however, the story is a bit different, and these coefficients aren't even statistically significant, okay? But ignoring that, even if you take the difference between these point estimates, you get a negative effect. So Head Start seems to have a negative effect compared to preschool on test scores for African American students. This doesn't mean that Head Start hurts their test scores. This means that Head Start doesn't seem to have a positive effect when compared to preschool. And the paper actually goes into this like general mystery, and it has a lot more results, and it also addresses this similarity of CY and CN, which is a really interesting part in the paper, but I'm actually not going to talk about that here. I think as a test of your understanding, you should go and try to read that paper on your own and see if you're able to understand it. I think that that's a really good paper. It should test your knowledge, and it's a good first one to go into, given that I've introduced the general idea of what's going on here. Otherwise, thank you so much for watching. I hope you enjoyed it. I hope you learned a lot. Maybe watch it again if you're a bit confused, but I will list my references right now, just in case you want to do some further reading on your own. So, the first book I referenced is Mostly Harmless Econometrics, an Empiricist's Companion. This is a very famous book in kind of undergrad and grad school economics. It's kind of a mixture between the like very theoretical econometrics textbooks and a kind of more practical, introduction to research design book that you might read. I think this is a good book, but it is a little bit heavy on the math, even more so. I would say it's mostly harmless, but still harmful, actually. I think this is a good second book to read, probably. We have Janet Curry's paper. I think you should try to read this next if you like this video. Then we have Bruce Hansen's Econometrics. This is the go-to book for econometrics, but it's very theoretical and it has very little intuition. If you're looking for a more theory-heavy source, I would recommend this book. Obviously, we have Minimum Wages and Employment, Case Study of the Fast Food Industry in New Jersey and Pennsylvania by David Card and Alan Krueger. If you want to read this too, I would highly recommend it. It's actually very interesting, and it goes into more depth than Currie and Thomas's paper. Obviously, it's different, but there's a reason this is the canonical 2x2 diff and diff design paper, and I would highly recommend reading it. I think the next book that you should read if you're interested in this is Causal Inference, the Mixtape. This is actually the kind of inspiration for that one graph and those tables that I used. I saw those also in Bruce Hansen's book, but in the form that I have, they're very similar to Scott Cunningham's book. This is a very, I wouldn't say easy book to read, but it is very intuitive, and I think it's probably better than Mostly Harmless Econometrics, and actually in some ways goes into more theoretical depth than Econometrics from Hansen, but in a more simple way. So this is actually a really good book, and if you're interested in this topic, I would recommend reading it. And a fantastic paper to read if you're interested in very recent work on difference and differences. I would recommend this paper by these authors, What's Trending in Difference and Differences, a synthesis of the recent econometrics literature. That paper goes into a lot of the stuff that we see here, actually. It kind of covers a lot of the recent work done, and maybe that I will end up presenting very soon. Hint, hint. Otherwise, thank you so much for watching. I hope you enjoyed. I hope you do some further reading. I hope you learned a lot. Thank you so much.